State and prove Taylor theorem. Now, what is Taylor's theorem? What is the statement of Taylor theorem? So, statement is, if a function fz, which is an analytic function within a circle C with center z0 and radius r. So this is an analytic function within a circle C with center z0 and radius r. Then at every point z inside C, fz can be written in the form of series. This series is written as n is running from 1 to infinity, an z minus z0 raised to power n. So where an is equal to this values. So this is the value of an. So this is the statement of Taylor theorems. Now, to prove this theorem, so what is the given part? So in the given part, there is some circle whose center is, so I am taking some circle whose center is z0 and radius is, so this is a circle whose center is z0 and radius is r. Now this is some circle with r radius and direction is anti-clockwise, and z is some point inside the circle C. So this is a circle C in which the function is analytic and z is any point inside the circle. If z is this point inside the circle, so we define another circle which lies inside this circle C. So this is a z is point on this circle. So this is a circle inside this C, and radius of this circle is small r and radius of bigger circle is C, and both have the anti-clockwise direction. Now what is given? So given is, if f is a function of some variable s, so this is a analytic within a circle C whose radius is capital R. So this function is analytic in this circle, inside the circle, and z is any point on a small circle, z is any point inside C such that distance between z and z0 is equal to small r. So this is equal to small r, and this is a point S. So this is a point S. So distance between S and z0 is capital R, and this is a small r. Clearly 0 is less than small r, and this is less than capital R. So clearly it satisfies these conditions. Now by using the Cauchy integral formula, so by Cauchy integral formula, a Cauchy integral formula. So what we get? We get f of z, because z is point inside this C, which is equal to 1 by 2 pi iota integration around C f of s over s minus z naught into ds. So this is some equation which is equation number 1. So here I am using the Cauchy integral formula. So z is any point inside the circle C, and it satisfies this condition by using the Cauchy integral formula. Now I will write this expression in term of this is z, here it is a, so just first write, so here it is a z, because here we take the point z. Now I will convert this expression in term of z naught. How we will convert it? So this can be written as f of z. So this is equal to, if this is a f of z, and this is equal to, so this is, so I write, so first I delete this term. Now f of z, this value f of z, this is equal to 1 by 2 pi iota integration around C, and this term can be written as integration this values, and this term can be written as s minus z naught minus z minus z naught, this values. So this can be written in this form, and this is f of s into ds. So this values. Now I introduce the point z naught. This can be written as in this way. Now this integration can be written as, which is equal to 1 by 2 pi iota integration C. Here it is f of s into ds. If I take s minus z outside, so s minus z is outside, so I get this 1 minus z minus z naught over s minus z naught. This is in raised bracket, and this is raised to power minus 1. So this is minus 1, and this ds should be outside this integration, because this term involved the value of s. So I am taking this term outside this integration. Now as we know that z minus z naught is equal to z minus z naught, this is equal to small r, and s minus z naught, which is equal to capital R. So R is less than capital R. So it means z minus z naught over s minus z naught. This is modulus is less than 1. So remember that, that's why I am taking s minus z naught outside. So this expression, this ratio, this common ratio of a GP series is less than 1. Now I can write in term of series. So in this way I can write it in term of series. So this value is equal to, now this is in next step, which is equal to 1 by 2 pi iota integration around C, and this value is equal to f of s into s minus z naught, and this is equal to, this is in term of series summation 1 plus, so here if I write in term of s z minus z naught over s minus z naught raised to power n, where n is running from 0 to infinity, this values, and this term is equal to into d of s. So this series can be written in this way, and we know that this is less than 1. Now if this is less than 1, so this series is convergent. So it is a convergent series because common ratio is less than 1, then that's why this series is convergent. So first, as we know that since modulus of z minus z naught over s minus z naught, this common ratio is less than 1. If this common ratio is less than 1, then it implies this series z minus z naught over s minus z naught raised to power n, n is running from 0 to infinity, is convergent series. So this is a convergent series. If it is a convergent series, then by using the Weierstrass M test, this series is convergent uniformly. So this is a convergent series. If it is a convergent series, we can interchange summation and integration. We can interchange this integration and summation because this is a converge uniformly. So this converge uniformly. If it converge uniformly, we can interchange this integration and summation, or we can say that summation can be taken it outside. If summation can be taken it outside, in that case f of z, which is equal to this values 1 by 2 pi iota into summation of n running from 0 to infinity, and then integration z minus z naught, this is raised to power n, and then this is by integration, this value will become integration of c f of s into ds over s minus z naught raised to power n plus 1, n plus 1. By using the Cauchy integral formula of nth derivative. So what is that formula? That formula is the fn z naught over n factorial equal to 1 by 2 pi iota into fs ds over s minus z naught raised to power n plus 1 around c. From this, this value is equal to 2 pi iota into this values. So 2 pi iota is cancelled with this term. Yeah, we can taken this 2 pi iota inside this values, 2 pi iota inside this values. So what we get? So we get, if this value is inside this equation, so this is, we cancel this values. So this value is this values. Now this value can be written as summation of n running from 0 to infinity. So what is the value of this, which is from this values? So this is a f nth derivative at the point z naught over n factorial into z minus z naught raised to power n. So this is a functional value of z. So in this way, we can represent the analytic function in term of a series, and that series can be written as f of z, which is equal to summation of n running from 0 to infinity nth derivative at the point z0 over n factorial into z minus z naught raised to power n. So this series is called a Taylor series or Taylor expressions. So this is known as Taylor series of function fz about the point z equal to z naught. So this is a Taylor series about this point. If z naught is origin means its value is equal to 0. So if z naught is equal to 0 means origin, in that case the series is converted as fz, which is equal to summation of n running from 0 to infinity nth derivative at point 0 over n factorial into z raised to power n. So this series is called a Maclaurin series. In that case, this series is known as Maclaurin, M-A-C-L-A-U-R-I-A-N, Maclaurin series. So this is called a Maclaurin series. Now, so in this way we can find the Taylor series as well as Maclaurin series from the Taylor series. To understand this theorem, so the statement of the question is obtain the Maclaurin series of the following functions. So obtain the Maclaurin series of the following function function. Number 1, A. So here function is e raised to power z. So this is an analytic function, as we know that, exponential function which is a analytic functions. If it is analytic function, so what is the Maclaurin series? Maclaurin series is f of z, which is equal to summation of n running from 0 to infinity, its nth derivative at 0 point over n factorial into z raised to power n. Now find the derivative. So first fz, which is e raised to power z, so f dash z, again e raised to power z, f double dash z, which is again e raised to power z, f triple dash z, so which is again e raised to power z. So f at the nth derivative of z, which is equal to e raised to power z. Now what is its value at 0? So f0 is 1, f dash 0 is 1, and continue the process at this point, which is equal to 1. Now this series f of z can be written as 1 plus, first is z over 1 factorial plus z square by 2 factorial, continue, plus z raised to power n by n factorial, plus so on up to infinity. So what is this? It is a e raised to power z, so which is equal to 1 plus z plus z square by 2 factorial plus so on, plus z raised to power n by n factorial plus so on up to infinity. So in this way we can find the Maclaurin series of the function e raised to power z. Now second part, similarly b part, here f of z is equal to sine of z. So what is this derivative? First derivative, which is cos z, second derivative, so which is minus sine z, third derivative, so which is equal to minus cos z. Now at the point 0, so f0, first term will be 0, f dash 0, 1, f double dash 0 equal to 0, f triple dash 0 is equal to minus 1. Continue the process. If we take f nth derivative, so at the even derivative its value is 0, at the odd values its derivative is, its value is minus 1. So it's raised to power 2n plus 1 derivative at point 0 is equal to minus 1. Now this will become a sine of z if I am using the formula of Maclaurin series. So this will be, first term is 0. So it will be started from z minus z cube by 3 factorial plus z raised to power 5 by 5 factorial, 1 positive, 1 negative, minus z raised to power 7 by 7 factorial, and so on up to z raised to power 2n plus 1 by 2n plus 1 factorial, these values. Now this term will be 1 positive, 1 negative. So this is raised to power, this is negative. So minus 1 raised to power 2n plus 1, these values. Now in this way we can find the value of this series. Similarly, for third is cos of z. So in this case cos of z, this can be started from 1 plus z, next term is 1 plus z, 1 and even term, z is this term will be 0. So 1 then minus z square by 2 factorial. So here I get the only even term. So 1 minus z square over 2 factorial, and then next term is positive z4 by 4 factorial. Continue the process up to infinity. This is cos of z. And next question is 1 over 1 minus z. So this can be written as 1 minus z raised to power minus 1. Now in the given part, thus it is a circle of radius less than 1. So if it is less than 1, then we can apply the binomial. So if we can apply the binomial, so this value is equal to 1 plus z square plus z cube and so on. This is possible when modulus of z is less than 1. Similarly, in case of 1 plus z, so this is equal to 1 minus z plus z square, then negative, then positive. So this is again possible when modulus of z is equal to less than 1. So in order to solve these equation, so we will check that when the modulus is less than 1, then we simply apply the binomial expansions. Now after that, the next is cos hyperbolic z and sine hyperbolic z. So if I take the example of cos hyperbolic z, so this can be written in the form of exponential. So what is the cos hyperbolic z? So this is e raised to power iota z plus e raised to power minus iota z over 2. So this is cos, and this is sine hyperbolic z. So this is 1 by 2 iota e raised to power iota z minus e raised to power minus iota z. So this values. Now we know the standard formula of sine, cos, exponential 1 over 1 minus z and 1 over 1 plus z. So I simply apply that result 1 by 2 iota, this is in bracket. So first is 1 plus iota z, first plus iota z raised to power 2 over 2 factorial and so on up to next, minus this, which is 1 minus this term, this is 1 plus, this value minus iota z, and next is plus minus iota z raised to power 2 by 2 factorial and so on up to infinity. This is in bracket and this bracket is closed. Now check that from this 1 is cancel with this one, and this is positive 2 iota z. So this is 2 iota z, and here it is this again cancel, this term is cancelled. So we get 1 by 2 iota, and this value is, first term is 2 iota z, this values. Now this will be cancelled, and second next term will be, this is 2 time iota z raised to power 3 over 3 factorial and so on. So what we get? We get z cube by 3 factorial. So this is iota square. So just simplify this result. So we get, so just so simplify the result. So we get z plus z cube over 3 factorial plus z raised to power 5 by 5 factorial plus so on up to infinity. So this is a value of cos hyperbolic z. So remember that in this case, this is the value of sine hyperbolic z. So remember that in this case, all terms are positive, but in the case of sine z, so one is positive and second is negative. Now similarly, we can find the value of cos hyperbolic z. So this is equal to 1 plus z square by 2 factorial plus z raised to power 4 by 4 factorial plus z raised to power 6 by 6 factorial plus so on up to infinity. So in this way we can find the value of this value. After that, the next question is, the statement of next question is, obtain the Maclaurin series, obtain the Maclaurin series of a function fz which is equal to z cube into e raised to power 3z, e raised to power 2z. So just using the standard function. So this is fz which is equal to z cube. So what is the standard expansion of e raised to power z? So this is 1 plus 2z plus 2z raised to power 2 by 2 factorial plus so on up to infinity. This value is equal to z cube, which is bracket. So this is not minus 1 plus 2z plus 2 raised to power 4 z square by 2 plus next term and so on. So this will become z cube plus 2z raised to power 4 plus 2 z raised to power 5 plus so on up to infinity. So in this way we can find the Maclaurin series by using the standard formula of e raised to power z or any other formula sin z, cos z, as well as 1 over 1 minus z and 1 over 1 plus z. So as per our requirement. After that, the next question is, find the series of cos of z about, now here about the point z is equal to pi by 2. Now my aim is to find a series about these values. Z is equal to pi by 2. How we will find it? So simplest way is, now here function f of z which is equal to cos of z. This can be written in the form of sine. That will z is convert into z minus pi by 2. So this will convert in this form as sine of pi by 2 minus z. So sine minus theta is equal to minus sine theta. So this can be written as sine of z minus pi by 2. So this value is written in this form. Now we know the series expansion of sine of z. So what is the series expansion of sine of z? So if I take in this way, so this is equal to sine of z. So which is equal to z minus z cube by 3 factorial plus z raised to power 5 by 5 factorial minus z raised to power 7 by 7 factorial plus so on up to infinity. Now in this case, if we take simple z is replaced by z minus pi by 2, so this value will become z minus pi by 2. This value will become sine of z minus pi by 2. So which is equal to z minus pi by 2 minus 1 by 3 factorial z minus pi by 2 raised to power 3 plus 1 by 5 factorial z minus pi by 2 raised to power 5 minus 1 by 7 factorial z minus pi by 2 raised to power 7 plus so on up to infinity. So this is the value of sine of this value. If we multiply by minus 1, so this will become a fz. So this is equal to minus this plus minus and plus. So this can be written as minus bracket. So this is in series, which is n raised to power 0 to infinity, and this is minus 1 raised to power n over 2n plus 1 factorial into z minus pi by 2 raised to power 2n plus 1, 2n plus 1. So this is the value of series. This is a expansion of sine of z about the point z is equal to pi by 2. So in this way we can find the Taylor as well as Maclaurin series.